So I'd like to welcome everyone to this session, and I'm the session chair, Ray Hong, from the University of Queensland, from Australia. And then this session is about CTR, advertisements, and click models. Today we'll have 4 full papers, 1 choice paper, and then 2 resource papers. So we're unlucky, many authors cannot be here because of the visa issues, so we'll have 3 proxy video playing and 1 proxy presentation, and then the others will be presented by the authors. All right, so we'll kick out this session. So the first one is the paper DDPO, Direct Dual Propensity Optimization for Post-Click Conversion Rates Estimation from authors from the University of Electronic Science and Technology of China and Hongzu University.
Good morning, everyone. Today, I'll share our recent work on post-click conversion rate estimation. In this work, we aim to mitigate the sample selection bias problem and predict the post-click conversion rate. In online advertising, the sample selection bias problem is a major cause of inaccurate conversion rate estimates. For better understanding, we begin by describing why the CVR prediction model is biased. Here, we show a typical sequence of user behavior in online advertising. Let's consider a little boy who wants to go play games with his friends. First, he opens a shopping site or app and searches for games as a keyword. Then the shopping site shows him a list of candidate items. In the field of online advertising, the term for this process is called impressions. This list containing all the candidate items is called the impression space, which is denoted as D. The little boy then clicked on the smartphone and gamepad among all the candidates on the site. Meanwhile, this behavior was recorded by the shopping site's logging system. All the click samples formed a new list. In the field of online advertising, this list of click samples is called the click space. We denote it by the symbol O. Finally, after the little boy's comparison, he chose to buy a smartphone. This behavior was also recorded by the shopping website. In the field of online advertising, the boy's purchase behavior is known as conversion. The space constituted by the items purchased by the boy is known as the conversion space, denoted by R. In order to learn from the boy's shopping behavior, the shopping site recommender system set conversion labels on items that the boy had clicked on. Conventional CVR estimation methods train the model in the click space O, however the inference space of the model is the impression space D. The discrepancy of data distribution between O and D leads to selection bias in conventional CVR models. To mitigate the sample selection bias problem, most of the Debian solutions utilize the inverse propensity score estimator or doubly robust estimator to eliminate the bias between click space training and impression space ground truth. However, these methods perform no direct optimization on unclicked samples due to the absence of conversion labels. To mitigate the sample selection bias problem, a natural idea is to train the CVR estimation model with both clicked and unclicked samples. However, there is a huge challenge in that the conversion of unclicked samples is unknown. This is because in general conversion can only take place after a click. This is exactly what motivates our research. We aim to optimize CVR models using both clicked and unclicked samples directly in impression space. To achieve this goal, we outline 3 critical issues in reducing sample selection bias. The biggest challenge is the absence of conversion labels since the conversion of unclicked samples is unknown. The absence of conversion labels for unclicked samples degrades CVR estimation performance and exacerbates the sample selection bias problem. The second challenge is impression space optimization. According to the previous introduction, we can realize that the impression space contains more samples than the click space. Optimizing the model with both clicked and unclicked samples in impression space ensures unbiased CVR estimation. Furthermore, previous studies have shown that failing to optimize on unclicked samples is prone to result in overestimated CVR. The third challenge is limited causal relationship. The click features and CVR features contain rich causal information that improves prediction performance. However, previous methods fail to exploit feature-level causality since they formulate the CVR and click propensity networks as independent models. To challenge these issues, we propose a novel solution to simultaneously optimize all clicked and unclicked samples in the impression space, named the Direct Dual Propensity Optimization Framework. This framework consists of three networks: the Click Propensity Prediction Network, the Conversion Propensity Prediction Network, and the CVR Prediction Network. These three networks share the same network structure and are all optimized in the impression space. In this framework, the Click Propensity Network is dedicated to ensuring that optimization in the click space is unbiased. This network is trained with both clicked and unclicked samples and predicts the click propensity of each sample. The Conversion Propensity Network is designed to generate pseudo-conversion labels for unclicked samples. This network is trained using clicked samples in impression space and then predicts the conversion propensity of all clicked and unclicked samples. In our method, the conversion propensity of unclicked samples predicted by this network is used as pseudo-labels to optimize the CVR model. The impression space optimization is designed to train the CVR prediction network. The CVR prediction network is trained in the impression space with both clicked and unclicked samples. It optimizes clicked samples using real conversion labels while optimizing unclicked samples using the conversion propensity. In our work to strengthen the causal relationship between clicks and conversions, we design a click causal transfer module and a conversion causal transfer module for the CVR task with the attention mechanism. Then, at the model optimization stage, we compute the loss function for each component network by the following sequence. We first estimate click propensity for each sample and compute the loss function of click propensity network. Then, we calculate the loss function of conversion propensity network and generate dynamic soft labels for each unclicked sample. Meanwhile, the causal transfer modules transfer the click propensity and conversion propensity information to the CVR prediction network. With generated pseudo-conversion labels for unclicked samples, we optimize the CVR prediction network with inverse click propensity scores in both click space and non-click space. After impression space optimization, we multiply click propensity by conversion rate to calculate click-through conversion rate. Finally, we sum the loss functions of all previous modules and optimize all components uniformly. After designing the overall optimization strategy for the whole model, we conduct extensive experiments on 5 public datasets and 1 private industrial dataset to validate our method. The experimental results verify that our method is able to significantly improve the prediction performance. From the results, our method is better at reducing estimation bias. We compare the prediction results of our method with previous state-of-the-art methods ESCM2 and DCMT. The ESCM2 is a typical causality-based method that optimizes the CVR model with only the clicked samples. The DCMT is a method that optimizes the CVR model with both clicked and unclicked samples in the impression space. According to the results, our method shows improved performance in reducing prediction bias compared to ESCM2, as evidenced by results closer to the label mean in multiple datasets. While DCMT's mean value is closer to the label mean in one dataset, it underestimates CVR values due to treating unclicked samples as 0, whereas our method demonstrates better overall performance and bias reduction across datasets. To demonstrate the effect of non-click space optimization strategies, we compare our method with 4 different strategies. DDPO is the proposed method in our work. Pseudo-0 refers to assuming that each unclicked sample is labeled with a conversion label of 0. CONVN0 refers to assuming that the conversion propensity of each unclicked sample is 0. Without NCLK is our method without the non-click space optimization. Without CONVN is our method without the conversion propensity prediction network. From the results, we are able to conclude that optimizing model in the non-click space is able to improve the performance. Furthermore, our method is able to outperform other strategies. In order to intuitively demonstrate the effect of causal transfer modules, we extract features from the penultimate layer of the CVR prediction network and calculated the cosine similarity between clicked and unclicked samples. In the visualization figure, the vertical axis represents clicked samples and the horizontal axis represents unclicked samples. A low similarity indicates that the clicked and unclicked samples are easily distinguishable. The results show that the similarity between clicked and unclicked CVR features is significantly lower in the approach with causal transfer modules. This observation verifies that the causal transfer module is able to transfer clicked and unclicked information to CVR features. Here, we also report quantitative results of 5 public datasets and 1 private industrial dataset. According to the results, our method is able to significantly outperform state-of-the-art methods by an average of 2.2% in terms of AUC. The results of the ablation study also demonstrate that each component of our approach contributes to performance improvement. Finally, to conclude, we propose the DDPO framework for directly optimizing CVR in the impression space with both clicked and unclicked samples. We experimentally verified that the conversion labels of unclicked samples should not be considered as 0. We experimentally verified that generating pseudo-conversion labels for unclicked samples is feasible and practical. We experimentally verified that integrating feature-level information sharing into CVR prediction tasks is beneficial for strengthening the causal relationship between clicks and conversions. That's all. Thank you for your attention. I'm open to any questions you may have.